In this video, we're going to look at a few more examples of infinite sequences. So the question here is to show that a sequence an is equal to 2n plus 1 divided by n squared plus n plus 1 is decreasing for n larger or equal to 1. Intuitively, we know that this sequence is decreasing because the numerator 2n plus 1 is a linear function while the denominator n squared plus n plus 1 is a quadratic function and hence grows faster, and that makes the ratio decrease. So the ratio, which is the sequence an is equal to 2n plus 1 divided by n squared plus n plus 1, decreases as n increases because the linear function grows at a slower rate than the quadratic function in the denominator. Now let's prove this formally. So the definition of a decreasing sequence is an plus 1. The successive term is less than the previous term. An plus 1 is less than an. This means that the sequence an is decreasing. So that means that 2 times n plus 1, but now n is n plus 1. So 2 times n plus 1 plus 1. So substitute n plus 1 for n, divided by n plus 1 squared plus n plus 1 plus 1 is less than 2n plus 1 divided by n squared plus n plus 1. So all of this is an plus 1. So basically substitute n plus 1 where you see an n. And this is an. We would like to prove this. All right, so let's simplify this. In the numerator, we get 2n plus 3. In the denominator, folding out the square sign, so we get n squared plus 2n plus 1 plus n plus 1 plus 1. This is less than 2n plus 1 divided by n squared. So basically we're just simplifying this. And so simplifying the denominator further, we get 2n plus 3 divided by n squared. And we have 2n plus n, that gives us 3n. And we have 1 plus 1 plus 1, that gives us 3 in the denominator. Is less than 2n plus 1 divided by n squared plus n plus 1. Now let's cross multiply, so we get 2n plus 3 times n squared plus n plus 1 is less than 2n plus 1 times n squared plus 3n plus 3. Now let's multiply all of this out and simplify. So 2n times n squared, that gives us 2n cubed, plus 2n times n, that's 2n squared, plus 2n, plus, now take 3 times n squared, that gives us 3n squared, plus 3n, plus 3, is less than 2n times n squared, that gives us 2n cubed, plus 2n times 3n, that's 6n squared, plus 2n times 3, that equals to 6n, plus, now distribute the 1, we get n squared, plus 3n, plus 3. We have to be very careful with simplification. So like terms combine, 2n squared plus 3n squared, and 2n and 3n, these are going to combine. So we get 2n cubed, plus 2 plus 3, 5n squared, plus 2n plus 3n, that's 5n, plus 3 is less than 2n cubed. So we have 6n squared and n squared, that gives us 7n squared. And we have 6n plus 3n, that gives us 9n plus 3. Now we can just cancel 2n cubed on both sides, basically subtract 2n cubed from both sides. And on the left-hand side, we have 5n squared plus 5n plus 3. And on the right-hand side, we have 7n squared plus 9n plus 3. So let's bring everything to the left-hand side. So we have 5n squared plus 5n plus 3 minus 7n squared minus 9n minus 3, less than 0. 3 cancels with 3, 3 minus 3 is 0. 5n squared minus 7n squared, this is minus 2n squared. 5n minus 9n, this gives us minus 4n. Clearly, this is less than 0 because n is bigger than, larger or equal to 1. Or equivalently, multiply through by negative 1, and we get 2n squared plus 4n is larger than 0. And this is a true statement for n larger or equal to 1. And if this is a true statement, then this has to be a true statement, which is an plus 1 less than an. Or equivalently, this is a true statement. An plus 1 is less than an. An plus 1 less than an. So we have proven that this is a decreasing sequence. All right, so what we have shown is that an plus 1 is less than an, which means this sequence, let me find some space here, this sequence an is equal to 2n plus 1 divided by n squared plus n plus 1 is a decreasing sequence, decreasing for all n larger or equal to 1. All right, let's look at another example. Does the sequence given by an is equal to minus 1 to the n, 2n divided by 3n plus 5 for n larger or equal to 1 converge or diverge? Notice that this sequence is bounded below by negative 2/3. Why is that? Well, that's because if we take the limit as n goes to infinity, dividing by the highest power, this part approaches 2/3, and it's bounded below by negative 2/3 because negative 1 to the n is either going to be plus 1 or negative 1, depending on whether n is a positive, whether n is an even integer or an odd integer. When n is an odd integer, negative 1 to the power of n is equal to minus 1. So we can see that this is bounded below by negative 2/3, and it's bounded above by 2/3, by plus 2/3, because negative 1 raised to an even power, that gives us 1. And when we take the limit as n goes to infinity of 2n divided by 3n plus 5, that gives us 2/3. So you can see that the negative 1 to the n factor oscillates between negative 1 and plus 1, because negative 1 raised to an odd exponent is equal to minus 1. Negative 1 raised to an even exponent is equal to plus 1. While the factor 2n divided by 3n plus 5 approaches 2/3 as n goes to infinity. Now, we took that for granted, so let's actually prove that formally. Let's take the limit as n goes to infinity of 2n divided by 3n plus 5. Divide by the highest power in the denominator, divide by n, divide by n, divide by n, and we get limit as n goes to infinity. 2n divided by n, that gives us 2. Divided by 3n divided by n, we get 3 plus 5 over n. 5 over n approaches 0 as n goes to infinity, and this ratio approaches 2/3. So you can see how this sequence is bounded above by plus 2/3 and bounded below by negative 2/3. And because the reason we have these two kind of limits is because we have the oscillatory factor negative 1 to the n that produces negative numbers, negative 1 when n is an odd integer, and plus 1 when n is an even integer. So this sequence diverges because for a sequence to converge, it has to have only one limit. It can't oscillate between two different limits. All right, so now let's look at how the terms of this sequence increase or decrease. So notice that when n is even, so for n even, when n is an even integer, an is equal to minus 1 to the power of n times 2n divided by 3n plus 5. And because n is even, negative 1 to the n gives us plus 1, so we get 2n divided by 3n plus 5. Now, does this increase or decrease? Let's consider the analogous function f of x is equal to 2x divided by 3x plus 5. Let's take the derivative applying the quotient rule, so we get f prime of x is equal to, square the bottom, we get 3x plus 5, all squared, take the bottom 3x plus 5, times the derivative of the numerator, which is 2, because derivative of 2x is 2, minus the top, which is 2x, times the derivative of the denominator gives us 3. Simplify f prime of x is equal to, we get 3x times 2, that's 6x, and we get 5 times 2, which is 10, plus 10, minus 6x. This 6x cancels out, we have 6x minus 6x. So the derivative comes out to 10 divided by 3x plus 5 all squared. Now it's clear that the derivative is positive. F prime of x is equal to 10 divided by 3x plus 5 all squared is larger than 0 for all x larger or equal to 1. That means the sequence is going to be increasing. So, and the reason is because if the derivative is positive, f prime of x is positive, this implies that the function f of x is increasing. That means f of n, the sequence f of n, is equal to 2n divided by 3n plus 5 is increasing, and we already showed that it's approaching 2/3. This sequence is approaching 2/3 by dividing by the highest power. We showed that earlier. So this sequence is an increasing sequence approaching 2/3. Now, let's look at for n odd. When n is odd, an is equal to minus 1 to the power of n times 2n divided by 3n plus 5. Now, when n is odd, negative 1 to the power of an odd integer gives us minus 1. So an is going to be minus 2n divided by 3n plus 5. But the same reasoning as before, we can use the derivative and show that f prime of x is equal to minus 10 divided by 3x plus 5 all squared, and the derivative is negative for all x larger or equal to 1. That means f of x is decreasing, because if the derivative is negative, it tells us the function is decreasing. So f of x decreases for all x larger or equal to 1. That means the sequence f of n is equal to minus 2n divided by 3n plus 5 is a decreasing sequence. It's decreasing and approaches negative 2/3. We can see it approaches negative 2/3 basically by taking the limit as n goes to infinity of minus 2n divided by 3n plus 5, dividing by the highest power and taking the limit, we'll get minus 2/3. So let's summarize. The even terms, an is equal to minus 1 to the n times 2n divided by 3n plus 5, the even terms of this sequence form an increasing sequence approaching 2/3, while the odd terms of this sequence, an, form a decreasing sequence approaching minus 2/3. So we can tell that the sequence an diverges. Why does it diverge? Because for the even terms approach 2/3, while the odd terms approach negative 2/3. So it is interesting to note that this is a bounded sequence. An is bounded above by 2/3, is bounded below by negative 2/3, but it's not monotonic, and that's why it doesn't converge, because it oscillates. And the factor minus 1 to the power of n causes the oscillatory behavior. This is what causes it in this case to diverge, because the even terms approach 2/3 while the odd terms approach negative 2/3. So the sequence an is equal to minus 1 to the n times 2n divided by 3n plus 5 diverges because the odd terms approach negative 2/3 while the even terms approach 2/3 as n goes to infinity. So it does not converge to a limit. It doesn't have a converging limit. It's oscillating between two limits, 2/3 and negative 2/3. And for that reason, it diverges. Now let's look at a graph. So we can tell that You can tell from this graph, we can label these. For example, this is A1 here. A1 is negative. Here's A2 is positive. A3 is negative. There's A4, it's positive. A5. So you can see how the odd terms are approaching negative 2/3. A6, and the even terms are approaching plus 2/3. Here's A7, and here's A8. I guess this is A9 here, and this is A10. Let's actually draw a curve through these sequence terms. So we have A1, A2, A3, A4, goes through A5, A6, A7, A8, A9, A10. So you can see how it's approaching. The even terms approach plus 2/3, the upper bound of 2/3, and the odd terms approach the lower bound of minus 2/3. This is a divergent sequence. All right, thanks.